This is the supplementary video for the paper titled Predicting Visible Image Differences under Varying Display Brightness and Viewing Distance. If we could predict what is visible to the eye and what is not, we could open possibilities for new applications. For example, when working with reconstruction algorithms, we could ensure that they minimize perceived differences rather than mathematical differences between pixels. Different from quality metrics, producing a single value representing the overall image quality, visibility metrics can predict a visibility map, which describes the probability of detecting a difference. Also different from quality metrics, visibility metrics account for viewing conditions like viewing distance and the display brightness. Existing visibility metrics are often not accurate enough, as they are white box models with too few parameters to learn the complexities of visual system. The recent work by Wolski et al. Showed that a CNN-based visibility metric trained on a suitable dataset can outperform white box metrics. However, the metric was trained for a fixed viewing distance and peak display brightness. Collecting visibility data requires tedious experimental procedures. Such experiments cannot be delegated to a crowdsourcing platform because the viewing conditions need to be strictly controlled. For these reasons, we had to find novel ways in which we train the metric. Firstly, we designed a hybrid architecture in which well-understood visual phenomena are accounted for with white box models, while the hard-to-model parts of visual processing are modeled using a black box CNN. We use a perceptually uniform transfer function to account for luminance masking, and resampling to account for a viewing distance. Secondly, we pre-trained the network with a large dataset generated with the existing white box visibility metric HDR-VDP. Although HDR-VDP cannot provide the ground truth data, it captures the right relationships and it helps to train the network. Finally, we collect an additional visibility dataset for varying viewing distance and display brightness. We use the dataset to fine-tune the metric. Firstly, we compare the proposed metric's performance against state-of-the-art methods. We select from our dataset a single scene measured at two different distances and two different luminance levels. The second row shows the visibility as marked by the observers in the experiment. The third row shows the HDR-VDP predictions. It can be seen that the predictions capture the right trend, but do not match the subjective data well. The last row shows the predictions of the proposed metric, which give a closer match to the subjective data. Secondly, we demonstrate how the predictions of the proposed metric vary with viewing distance and with the peak display brightness. The proposed metric correctly predicts loss of visibility with the increasing viewing distance and with decreasing absolute luminance levels. Thank you.